Hey folks, welcome to my channel, Number Pen. So we have the problem on our screen. Prove that f of x equals 2x squared plus 3x minus 5 is continuous at all points in R, right? So in this video and in the subsequent videos, we will look at problems on continuity, right? And before that, I thought I'll quickly run through the three basic requirements that will have to be satisfied when you check for the continuity of a function y is equal to f of x at x equals to x naught, right? So x naught is some point that belongs to R, right? And what is R? R is nothing but it is the set of all real numbers, right? And what do we mean by the set of all real numbers? All the numbers in the open interval minus infinity to plus infinity, right? Which means it does not include minus infinity and plus infinity, but it includes all the real numbers that belongs to the open interval of minus infinity to plus infinity, right? So let's write that down. And before we actually begin to discuss these three requirements and apply them in this particular problem and solve this problem, right? So let me start off with the first requirement, right? So what does it say? F of x must be defined in a neighborhood of x naught, that is f of x naught exists, right? So when you see the function f of x, the function at all points, when you just do a substitution, uh, pick up any number belonging to R, right, which is again the set of real numbers, and do a substitution in y is equal to f of x, then f of x has to be a finite number, which means it will also be a real number. So that is what we mean by must be defined in a neighborhood. So which means it cannot be infinite. That is point number one. Second, it also cannot be undefined, right? So it cannot take an indeterminate format. So which means f of x has to be a finite number belonging to R, and it must be defined in the neighborhood of x naught, means f of x naught exists, right? So so that is point number one, and let me do a simple tick off the point that we have discussed, right? And now we'll come to the second point, which is limit extending to x naught. F of x exists, right? Now, whenever we've been asked to find out the continuity of a function at a point x equals to x naught, once we take a look if f of x is defined at x naught, the second important step that we actually need to take is to see limit extending to x naught f of x exists, right? And why is this? So what do we actually mean by continuity? Continuity, when I you pull out the English dictionary meaning, right? What does continuity mean? It means being continuous, right? And what does it mean being continuous at a point x equal to x naught? All that it means is when I approach x naught from the left, right, which means I take a value which is very close to x naught, but I'm approaching it from the left, then the function has a finite limit as x tends to x naught from the left, right, which is my left hand limit. And when I do the same thing from the right, which means that x is tending to x naught, but this time it is tending from the right, then still there is a limit that is existing, and the limit is a finite limit, which means, and both these values are equal, right? So limit x tending to 0 x naught, left hand limit is limit x tending to x naught minus h, right? And h is infinitesimal tending to 0. And similarly, limit x tending to x naught plus h, which is nothing but your right hand limit, which means that we're approaching x naught from the right hand side. Both of these limits are equal and they exist and they are finite, right? So that's the second point. So what does it actually mean? Which means that the graph of this function at a particular point x equal to x naught is continuous, which means there is no break in the function at x equal to x naught. And how do we determine that mathematically? One way is to quickly plot the graph and take a look at whether it is continuous at that point. But when you want to do this mathematically, what we do is we arrive at the limit of that particular function, both the left hand limit and the right hand limit of that particular function at x equal to x naught, and see if they exist and they are equal, right? So that is the second point when it comes to checking the continuity of functions, right? So let me do a tick here as well. So the first point, f of x exists at x equal to x naught, right? So which means f of x naught exists. The second point is, as we approach x naught from the left or the right, we have a limit that exists for this particular function y equal to f of x. Now, the third condition is nothing but a combination of condition 1 and 2, which is for the function to be continuous, we have f of x naught equal to the limit as x tends to x naught, right? Which means the function, like I mentioned earlier, does not have a break at the point x naught, which means if I take a value which is very close to x naught, be it from the left or be it from the right, I can confidently say that f of x naught equals to limit extending to x naught f of x, right? So, which actually means the graph of the function does not show a break at x equal to x naught, and it is a finite number, right? So, this is the third condition for continuity of a function y equal to f of x, right? So I'm just repeating the three conditions again. One is f of x, the function itself has to be defined at a particular point x equal to x naught, right? And the second thing is whenever x tends to f naught x naught, be it the left hand limit or the right hand limit, then we have a finite limit that exists for this function, right? Which is limit f of x exists at the point x equal x tending to x naught, right? And thirdly, the f of x naught in condition 1 and the limit extending to x naught in condition 2 both will have to match and they will have to be equal, right? So these are the three important conditions to be satisfied for the continuity of a function y equal to f of x at x equal to x naught, right? So with this, let's proceed about solving the first problem under continuity which we have on our screen, right? So prove that f of x equals 2x squared plus 3x minus 5, right, is continuous at all points in R. So what is our first condition, right? F of x must be defined in a neighborhood of in the neighborhood of x naught, right? And let me remove all these tick marks because let's do that for this particular problem and see whether we meet all the conditions, right? So f of x must be defined in a neighborhood of x naught. That is, f of x naught exists, right? So what does that mean? So when you look at this, this is a polynomial function, right? So let us write that down. And R means open interval of minus infinity to plus infinity. R is a set of real numbers. When you say real numbers, it could mean integers, it could mean fraction, it could mean positive numbers, it could mean negative numbers. It involves all the numbers which are between minus infinity and plus infinity, but those are finite numbers. That's why we show them in the open bracket here, which means that they belong to the open interval minus infinity to plus infinity, right? So let me write down this particular equation. And when you do a substitution, right? So let's say, let's pick up any number in the interval, right? Let's pick up any number C that belongs to the interval of R, right? So, so C is nothing but the equivalent of x naught, which we discussed, while discussing the conditions for continuity, right? So what is f of C, right? Now f of C is nothing but 2c square plus 3c minus 5, right? And if c takes a real number, what does f of c take? Now, is there a possibility for f of c to become undefined or infinite? The answer is no. As long as c belongs to the set of real numbers, we know that f of c will always be defined, right? Defined. F of c defined for all c belonging to R, right? And that means R first condition is sorted out, right? So the first condition that f of x must be defined in the neighborhood of x equal to x naught is sorted out for r, right? So let's put a tick mark here. The second condition is, let's move to the next line, and we've been asked to find the limit x tending to x naught f of x exists, right? So let's pull out the limits and let's evaluate the limit as x tends to. In this case, we've just taken the number c belonging to the set of real numbers, right? Now, if I want to take out the right hand limit, then I do limit extending to h, and where your h is infinitesimal 0, right? So when I write this like this, what do I get? I get 2 times c plus h the whole square, and plus 3c plus h minus 5, right? And let's expand c plus h the whole square and rewrite it. And what do we get? We get c square plus h square plus 2ch. And when I expand my 3c plus h, all that I get is 3c plus 3h, right? Now we know that c can be any number belonging to r, right? So which means when I do a replacement of h equals 0, what do I get? Let me move to the next line, folks. All that I get is h square becomes 0. My 2ch is 2c into 0, which becomes again a 0. So this part, h square plus 2ch, let me highlight it in yellow, becomes 0. And similarly, I have my 3h also becoming 0, right? So I can remove this as well. And so what do I get? 2c square plus 3c minus 5 is what I'll be left out with, right? So this is, so I'll be left out with 2c square plus 3c. So once you do a substitution of h equals 0, you arrive at the limit. And what is that limit equal to? 2c square plus 3c minus 5, right? And why is that? We've substituted h equals 0, uh, and we notice that h square plus 2ch, which is the yellow term highlighted on your screen, and similarly the 3h, which is the other yellow term, all become 0, right? And so we are left with 2c square plus 3c minus 5, right? And now, very similarly, right? And I'm not going to repeat the step here. Very similarly, when you do c minus h, which is your left hand limit, right? C minus h. As a quick check, what we do is we replace c with c minus h and try and check out what will be the limit when we have c minus h. So all that we are doing is we are picking up a number which is very close to c, but which is smaller than c, and that is why we are representing it as c minus h and h tending to 0, right? And here we have, when I do that, I have 2 times c square plus h square minus of 2ch plus 3c minus 3h minus 5, right? And what happens when I do a substitution of h equals 0? Again, my LO term, which is h square minus 2ch, and my 3h become 0, right? And I'm left with 2c square plus 3c minus 5. And what does that establish? My limit, so let's call it my LHL or the RHL, which we initially worked out. Both of them are equal, and they take a value 2c square plus 3c minus 5 at the point x tending to c, right? So that is what we uh, we have established, which means that our condition 2 also is fine, right? And look at this, folks. LHL or RHL will be a finite number for any C, right? Provided C belongs to R. And that is what we've been asked to establish. We've been asked to establish the continuity of this function at all points in R, which means it does not include the minus infinity or the plus infinity, right? So which means my condition 2 is also satisfied. So let's put a tick here, right? And now I don't have to do anything special or anything additional for checking condition 3, right? All that I have to do is check what is the value at f of x naught, which is, we have called it c in this particular case. What is that? That is nothing but 2c square plus 3c minus 5. And what is my limit x tending to c, f of x, right? It is nothing but 2c square plus 3c minus 5, right? And are these two values equal is what we need to check for the third condition, right? And what is that? So we notice that both this and this are equal, right? So which means our condition 3 is also satisfied, right? So f of x equals 2x squared plus 3x minus 5 is indeed continuous at all points in R, because it satisfies all the three conditions at any point C, provided C belongs to R, right? So that is how you go about proving the continuity of y equal to any f of x, right? So I hope you found this video useful. Please do subscribe to my channel and support. Thank you.